So today we're going to take a look at section 5.4, part 1, which is on logarithmic functions. Okay, so logarithmic functions are basically the inverse of exponential functions. Okay, in a way, they're kind of opposites of each other. All right, so keep that fact in mind as I show you the next couple things. Okay, logarithmic functions are inverses of exponentials. Okay, I want to mention the idea of what's called the horizontal line test. Okay, you've probably done the vertical line test, which says if you draw a vertical line on your graph and it only hits it one time, no matter where you draw it, your graph is a function. Well, the horizontal line test is similar, except it says if you take your graph and you draw a horizontal line and it only hits it one time, then the inverse is a function. The inverse of your picture is a function. All right, so let's look at this. So exponential functions pass the horizontal line test. So they look something like this. They curve up very quickly, and no matter where I draw a horizontal line, could it ever hit it more than once? No, not on an exponential. Okay, so if exponential functions pass the horizontal line test, and logarithmic functions are the inverse of an exponential, what does that mean? So if exponential functions pass the horizontal line test, and those are the inverse of logs, what does that mean about logarithmic graphs?
They're not a function.
They're what?
It is a function.
They're functions, yeah. Right? They are functions. If exponential functions are the inverse, and they pass the horizontal line test, then logarithms are functions, because logarithms are the inverse of exponentials. Right, so when we graph it, a vertical line will only hit a logarithm one time. Okay, and we'll look at some graphs in a little bit. Okay, basically, the idea, if you were to graph both a log function and an exponential, they're mirror images of each other over the line y equals x. Okay, so they're not mirror images over an axis. They're mirror images over this. If you put that line in and mirror image something over that, we'll get this picture. Okay, so in blue is an exponential. Okay, in red is a logarithmic. And you can see if you flip it over the line y equals x, they land on top of each other. They're mirror images. Okay, does everybody see that? Any question on that? All right, you could do the same thing with like half of a parabola and a square root function. Those would also be mirror images of each other, because squaring and square rooting are inverses. Okay. All right. So next thing I want to look at is how we pronounce this equation that has the word log in it. Okay. So the way you say it is y equals log base a of x. Y equals log base a of x. And if you were writing it on lined paper, it would look something like this. Okay, so there's your y equals. You'd have the word log, and the base a is a little bit below. The x is right on the line. Okay, I don't want you to think that the x is an exponent. It's not. It's right on the line with everything else. This would be an exponent if you put a 2 up high. Right, so it's log base a of x. And x is called your argument. Okay, that's just the thing that you're plugging into the log function. Right, just like if I did this. We could call 5 the argument. It's the thing I'm plugging into the square root function. Okay. if the base happens to be 10, okay, we give a special name to that kind of log. Okay, that's called a common log. Okay, there's two logs that have special names. This is one of them. If the base is a 10, we call it a common log. And because we use base 10 a lot, sometimes they don't even write it. Okay, so if you just see log, okay, and then you have your argument, and there's no base written, we assume the base is 10. So if I asked you to figure out what is the log of 7, okay, I'm assuming here a base of 10. Log base 10 of 7. And the calculator can do that. On the calculator, if you wanted to find the log of 7, you just press log 7, and that's the answer. And notice it doesn't write the base either. Okay, so it's assuming that we want a base 10.
How do you change the base?
We'll talk about this. One other base the calculator can do, there's a button for it. But if you want to do something other than those two, we'll learn that next time. Okay, there is a way you can type in any base you want, but I'm going to save that. It's a little bit of a formula, so I'll save it for next time.
So you're just going to be doing common log for now?
Common log and the log where we also have a base of e. Okay, we talked about this a little bit yesterday. Did anybody remember what I called this one? This wasn't the common log, it was the Brad? Natural log. Okay, so anytime you have a logarithm with a base of e, that's called the natural log. But a lot of times you're not going to see it written the way I have right here. Log base e. In fact, most textbooks you'll probably never see that. The reason is there's an abbreviation for it using the first two letters of natural log. Okay? You might think, well, they'll just use the NL, but they actually switch it. Okay? I don't know why. So they call it LN. That's the abbreviation for this. So this and that are exactly the same thing. LN is just a shorter way of writing log base e. The other thing you got to be careful when you write LN, the base is hidden. You have to remember that it's a base e. Okay? So in that abbreviation, it hides the base. So LN is the same as log base e. So if I asked you to find log base e of 2, what would that be the same as writing?
ln2.
Yeah, the natural log of ln of 2. Okay, and your calculator has a button for this one as well. Okay, this one is right below log. ln, lowercase l, lowercase n, 2. Okay, so your two log buttons that we're going to use, they're right by the 7 and the 4. Log and ln. Okay, any questions on that? So let's take a look at a picture and see why these are the domains and ranges. Okay, let's just grab log of x. And I'll start with zoom 6. So on the domain, it starts at 0, but you can't include 0. If you try to take the log of 0, you'll get an error. Okay, you can't do log of 0. But you can pick any number from 0, and you can go as high as you want. Now the range, it says negative infinity to infinity. Okay, what's really happening, let's see if I can get the picture up. And you can't see it on the screen. But that line is really dropping way down. Okay, it's actually doing something like that. Okay, and the reason we can't see it on the screen is because the calculator can't graph things that are almost vertical. Right? But if I type in something extremely close to 0, try like 0.00001 a bunch of times, you can see I'm at -12. Okay? It doesn't go down very quickly. If you wanted to get a number that was in like -200, you'd have to type 0.0 200 times and then put a 1. Yeah, you can. Have fun. But you can see it does go down forever. And it goes up forever, but it goes up very slowly. Watch if I let x be 100. Even if I let x go all the way to 100, y is only at 2. If I let x go all the way to 1,000, it still isn't going to go up that much more. Y is only at 3. Okay, so remember I said about exponential functions. They were some of the fastest growing. Well, what do you think these are? These are the slowest, okay, because these are the inverse. So logarithmic functions are the slowest growing, because we're all the way at 1,000, and y is only at 3. Okay? Even if you went to 1,000,000 on the x-axis, this still wouldn't go off the screen. No, wouldn't go off the screen.
So does it ever stop going up or not?
No, it never stops going up. It just goes up extremely slow.
So eventually you get like 1,000,000.
To hit 1,000,000 on the y-axis, well, yeah, you have to go way out. Because even if I go to 1,000,000 on the x-axis, watch how high it is. It still isn't off the screen. It only goes up to 6.
Yeah, zeros.
Yep, so it's a very, very, very slow growing function. Okay, and remember, this part here would curve down like that. Okay, so just remember that part does curve down. Okay, any questions on the domain or range? Okay, so make sure you know it, because you can't really get it by looking at the calculator and completely understand it, because the picture is not accurate. That picture is accurate. All right, next thing we're going to do is convert between two different types of equations. We have what we call logarithmic form and exponential form. And here's our equation. We can change from one to the other. Okay. For this to work, we have to have a base on our log that's greater than 0. Okay. We're not going to deal with negative bases because that gets into imaginary logs, which you can do, we're just not. And the base is not equal to 1. Okay, but any positive real number other than 1. Right, and it's basically just a pattern of looking at what goes where. Right, so this a we call the base on our log. But when I rewrite it in exponential form, it's still the base. Okay? It's going to be the thing that has an exponent written higher. Okay. The next thing that I think will help you kind of remember where the y goes is logs are exponents. Logarithms are exponents. So anytime that you want to solve for an exponent, like in a problem like this, if you wanted to figure out what x is, you have to use a log. Logarithms solve for exponents. All right. So in this one, my logarithm equals y. This is an exponent. Logarithms always equal, or always are, exponents. So y becomes the exponent. Well, once you've used the a, you've used the y, there's only one thing left to use, and there's only one spot left for it to go. Right, so we're going to practice using that formula to change back and forth. Okay. Does everybody have a formula? All right. And it's not hard. It's just a process of learning what goes where.
Can you restate what you just said about logs are exponents? I didn't get it.
So if I had a problem like that, and I wanted to solve it, okay, the way I would solve it is with a logarithm. Anytime you want to solve for an exponent, you use a logarithm. Okay, let me show you how you would solve this one, just to kind of show you the point. Okay, don't worry about how I'm doing it. I'm just going to get x by itself. So this would be that's the answer to that problem. So anytime you want to solve for your exponent, it's going to equal a log. So that's why I said logarithms always equal exponents. Logarithms are exponents. Okay? That's what they're used for. Okay. How you would type this into the calculator, we don't even know yet, because it's a base 2. We only know how to type in what two bases? Yeah, natural common, 10 and e. Okay, so you wouldn't know how to type this in yet. It's very easy once I show you.
So like the 10 to x.
What's that?
Is it like the second log button?
We could use that 10 to the x for different things if we wanted to. It's basically just a quick way to type 10 to a power, like 10 squared or something. But we don't really use it that much. But no, we won't use that one. All right, so let's try to rearrange this so we get it in exponential form. Okay, so first thing that's going to happen is the word log is going to disappear. Okay, Tom, what's my base here? Think in how you would pronounce this. You'd have to say
3.
base somewhere. Yeah, 3 is my base. Base is the number that's lower than everything else. Okay, 3. Okay, and Heaven, logarithms always equal what kind of number? No, not a, let's see. Yeah, in most cases it'll be a real number, but what are logarithms used to solve for? Yeah, logarithms always equal the exponent. Okay, so that becomes your exponent. And DJ, what's the only thing left? X. So that's how you rewrite the expression above in exponential form. We can't solve this because we don't know y and we don't know x. If we knew one of them, we could figure it out. Right, let's try this one. Okay, Olivia, what's my base here?
5.
Yep, 5. And Graham, my exponent?
Y.
Yep. Logarithms always equal your exponent. And once you figure out where those go, you only have one thing left. What's left? X. That's it. So that's exponential form, started in log form. Okay, questions on that? Okay, that's kind of the basic idea of what we're going to do today. Is lots of little things like this. Simple things, but there's lots of them. Okay, now we'll try the other way. Take something that's in exponential, change it to log. Well, if I'm going to change it to log, the first thing I should do is write down the word log. Okay. Shelby, what's my base going to be? And if you get stuck, think about what your base is in that example.
1.2.
Yeah, base is the thing that's below the exponent. So my base is 1.2. Okay, and Brad, logarithm always equals what kind of number? The exponent. And what's my exponent in this case? 3. And the last thing I need to fill in is my argument. Right? So it's the only thing I haven't used. Yep.
I said
M, yeah. So that's our answer. Questions on that? What's the name of this thing again, the M? Yeah, that's the argument. All right. E to the B equals 9. Okay, so just the same as last time, first thing I should write down is,
Okay, the whole thing, just the one part.
okay, you can do the whole thing?
Can I try?
All right, go ahead.
Okay, B equals log base E.
log base e of 9. Okay. Now, the only thing here, we talked a little bit about maybe an abbreviation we can use. This is correct, but I just want to go one step further. B equals, how can I shorten this up a little bit? ln of what? 9. So 9 is the argument to my natural log function. Now, if we wanted the answer, we could go on the calculator. We could type in ln of 9 and see what it is. But for our purposes, we don't need to find the decimal. And let's try one more. A to the 4th equals 24. Okay, anyone think they can give me the whole thing? Yep.
Log sub A, is that it?
Yeah, base A.
Base
Yep.
A. To 24
Yep, of 24.
Of 24.
So log base A of 24
equals 4.
equals 4. Okay. So any questions on changing from exponential to log?
Can you just like read it again? Log base A.
Log base A of 24.
So sub A is wrong.
Yeah, I've never heard it read that way. Maybe some people do, but.
Sorry.
It's only a question in chemistry. So,
Oh, log sub A? Maybe.
I guess that's good.
Yeah, it is a subscript. I know a lot of times when we say like, x1 and y1, I guess you could say y sub 1, x sub 1. I've heard that kind of in that context, but I've never heard sub used in log. Doesn't mean it's wrong, but I've just never heard it that way. All right, this one I want to show that what's on the left and the right are the same. Okay, so I have an equation here. What format is this called? Yeah, it's logarithmic form. The only thing I know how to do is change it to exponential. So if that doesn't work, then we're stuck. Okay, so let's just try it. Okay, DJ, what's my base? 2. And heaven, my exponent? 3. Logarithm always equals the exponent. And what haven't I used? 8. What's 2 cubed?
8.
Yeah, so 8 equals 8. Yeah, that works. So we showed that log base 2 of 8 does equal 3. Okay, next problem is the same idea, except I'm not telling you what it should equal. I want you to figure out that part. All right, so how would we rewrite this one? Yeah.
5 to the x.
Yep, 5 to the x
Equals 125.
equals 1/25. Okay, now at this point, we just have to look at it and figure it out. Okay, I wouldn't have given you a number that wasn't a power of 5 here. Okay, if I put 1/24, you'd have a very hard time with this problem. Or 1/26, it had to be 25, okay, or some power of 5. Think of this problem. Okay, what if you had that? What would the answer be?
2.
The answer would be 2. Now, we don't want to get 25. We want it to flip. So think what kind of number would make this flip? A negative. Okay. So if you want it to flip, look at your power. Think what you'd have to raise 5 to get that not flipped, and then make it negative. Okay, negative 2. Okay, questions on that? Right? Let's try solving this one. Log base 5 of x equals 1.5. Okay, Shelby, how could I rewrite this?
confusing me.
Confused?
Yeah,
All right.
like I'm okay going from like the exponential to the log.
Oh, the other way? Yeah.
Yeah.
So what do we call this thing right here?
Like the subscript. The base.
The base, yeah. So when you rewrite it as an exponential, we always have a base, you have an exponent, and then you have a spot for the thing we haven't used. Okay, so we've got our base, and now a logarithm is always used to find what kind of number?
What's the argument, right?
What do we always use logarithms to solve for? I said logarithms are
Exponent.
exponents. Okay, so your logarithm always equals an exponent. So that part becomes your exponent.
And then it would just equal the x.
Yeah, that's the argument. Okay, when you rewrite it, the base, exponent, argument. Okay, and now this is something we could just type it in and see what we get. Okay, so it just takes a little practice with learning to rearrange it, and you get used to it. So it's about 11.18. Okay, so in that example, what we solved for was in the argument. Let's look at an example where now what we're going to solve for is in the base. Right, anybody tell me how I can rewrite this one? Matthias?
X to the second power equals 3.
Yeah. X to the second power equals 3. Right? Now, earlier I gave you very early on, gave you a restriction on the base. What kind of number does the base have to be?
Greater than 0 but cannot equal 1.
Yeah, the base is, you said it somewhere, right here. A is greater than 0. Okay? So, when we're solving this, keep that in mind. Okay, what do I have to do now to get x by itself? Take the square root. And normally, how many answers do we get when we take a square root?
2.
2.
Show me its roots.
But we're going to ignore which one here?
The negative.
We're going to ignore the negative because we just said the base has to be positive. So don't write the negative answer. Okay, if you did, we'd be getting into imaginaries with logs. Okay?
Wait, what would happen if the base was 1?
If the base was 1, some of these, let's go back here. If the base was 1, this isn't really an exponential expression anymore on the right. Think about if I wrote 1 to a power. Is that exponential? So no, I can't really call this exponential form if a is 1. And I'm actually going to answer that a little bit more directly in a minute. If the base, well, actually, I'm going to answer when the argument is 1, not the base. So, but yeah, that's why. Okay. Any questions on that one? Okay, so you can solve for the variable in all 3 spots, whether it's in the base, whether it's the argument, or whether it's an exponent, okay? Or whether it's by itself on the other side. Okay? You can put the variable in any of those 3 spots. All right, so next thing we're going to look at is some properties of logs. Okay, these are basically special patterns. There's not really any arithmetic or algebra you have to do. You're going to see a special pattern, and you just have to recognize the pattern. That's all. Okay, so here's our first pattern. If you have something written like this on the left, a to the log base a of x. Okay, let me do an example with numbers. 3 to the log base 3 of 4. Okay, and I ask you to simplify that. If these 2 numbers match, okay, the base on the log and this base here, what basically happens is they cancel each other out. And all that you're left with is whatever's right there. That ends up being your answer. Okay? So if we look at my problem, the base on the log and the base here match. So those cancel out, and what's left is my answer. 4, that's it. That's all you have to do. So you're just recognizing a special pattern. Now, if this one was a 3 and this one was a 2, this pattern doesn't work. These numbers have to match, and they cancel each other out. Yes?
So if those, like if the A's were the same, wouldn't the X just be the same on both sides? Can't you just infer that from the beginning?
Yeah, so if the A's are the same, whatever's right there is your answer. That's the final answer. Okay, here's another special pattern. It says log base A of a to the x equals x. Okay, so if the base on my log matches the base on my argument, it's like these things cancel each other out, and whatever is right there, that's my answer. Okay, we'll do a numerical one with that in a little bit. Okay, but this one, and I could do it for the other one, but this one I want to show why it works. Is this a log equation or exponential? Yeah, it is a log. There's my base. There's my argument. And there's what's by itself on the other side. Okay, so what did I just say my base was? A. Okay, so I'm going to rewrite this in exponential form. And that's going to show me why it's true. Okay. Logarithm always equals what kind of number? That's my exponent. And what goes on the other side by itself?
The argument. A equals A. I mean, I can't talk.
A to the x. Okay, so all that this rule is saying is that something equals itself. Okay, you might have learned that in other classes as the reflexive property. Something always equals itself. This is just a way to write it as a log, okay, rather than x equals x or something like that. Okay, so any questions why that's true?
So the answer is if it's...
Yeah, this is just like, it's like a proof.
Yeah.
This is the reason why rule number 2 works. So I just took rule 2 and rewrote it in exponential form to make it clearer, show you why it works. Okay, I'll do the same thing here. Log base A of A equals 1. So if I asked you for log base 2 of 2, the answer would be 1. Log base 7 of 7, the answer is 1. Okay, Brad, what's my base here? Yeah, which one? The one that's higher or lower? Yeah, that's my base. So put that right there. Okay, what's my exponent, Shannon? The 1. Logarithm always equals your exponent. Put that there. And what goes on the other side? The A. Okay, so this formula says that if you raise anything to the first power, you get the same thing back. Okay, raising something to the first power, it stays the same. That's all that this rule says. I think it's a lot easier to see it in exponential form, more familiar, than in log form. Okay, any questions on that one? Right, and the last rule. If you take the log and the argument is 1, doesn't matter what the base is, the answer always comes out to 0. So log base A of 1 always equals 0. Okay. Now I've gone through a couple. Can anybody help me rewrite this in exponential form? And I guarantee this is a basic rule from Algebra 1 that hopefully you remember. Brad? Yeah. Anything to the 0 power equals 1. It's just written as a log rule rather than how you learned it in Algebra 1. Okay. Any questions on that one? All right, so we're not going to, I don't expect you to go through the proof. Okay, on the test, you don't have to show me why. You're just going to have something like this. And I'll ask you to simplify it. Okay, which rule does this one look like? Out of 1 through 4?
First one.
Yeah, it's the first one. where those two numbers match. So if you were to simplify that, what would you get for an answer? Yeah, you get pi. That's your answer. That's it. Okay, that's all you have to do with that kind of problem. Okay, how about B? What rule does that look similar to?
Second one.
Yeah, that looks like the second one. So if I were to simplify this one, what would I get?
-4.
Yeah. This would cancel out, and the answer is whatever the exponent is, -4. And how about this one? ln of e to the kt. It's a little tricky. Anybody see what rule that one looks like? It's hidden. We're going to have to maybe rewrite something first, and then you'll see it very clearly.
Is that the second one?
That is the second one, yeah. What can I rewrite here to make this actually look like the second one? Because I think some people still probably don't see how to do that.
Log base e of e k.
Yeah. Rewrite ln the long way. Log base e. What I just circled in green, those two things are the same. And now copy down the rest of it. E to the kt. So now we have the base on the log and the base on the argument matching. So what would that simplify to?
K.
Yeah, k times t. Whatever k times t is. All right, so that's a little tricky because the base is hidden and you have to rewrite it first. Or after a while, you might just see it in your head, and that's fine too. Let's see, I didn't have an example for properties 3 and 4. Just make one up for property 3. Log base 4 of 4. What would that be? 1. Anytime your argument and your base are identical, the answer is always 1. Okay, anyone need an example for the last one? Just put in any number you want for A. All right. And last thing. Okay, so the last thing we're going to do is combine logarithms, or we can split them. We can do both. We can kind of think of it like combining like terms. Okay, here's one rule that we can use to combine logarithms or split them. You can look at it either way. This rule says log base A of the product m times n. If you have a product, you can split that as a sum. A product splits as a sum. In each part of the sum, we have a log and a log. The base is exactly the same all the way through the problem. It started as base A, base A, base A. Okay, the base never changes. My first argument is my first factor, and my second argument is my second factor. So there's an example with numbers. Generally, you wouldn't do this. You wouldn't write this out with numbers. You do it with variables. Okay? But I'm going to show it to you with numbers so I can actually plug it in on the calculator, and I'll show you it works. Okay, so I'm going to type in log of 4 times 5. Okay, and I get 1.30. Now I'll type in log 4 plus log 5. Okay, what base am I using the way I'm typing it in? Yeah, I'm using 10, but I could use any base I want. It's just 10 is the fastest for me to type in quickly. Okay, it comes out the same. Anybody think of another one that would come out the same? Think of what 4 times 5 is, and think of another way you can break that up besides 4 and 5. Yeah, you could do 2 and 10. Any two numbers that multiply to give you 20. 2 and 10. Okay. So a product splits as a sum. What do you think a quotient splits as? Yeah, it's a difference. Okay. It's 2 logs. The base is the same as the original. The first argument is the numerator. The second argument is the denominator. Okay, and I'm not going to go through the calculator one this time, but if you want to see it with numbers, if you had log of 4/5, you could write it as log 4 minus log 5. And again, any base you want, even base e. So this would work with ln's. Okay. And the third rule. Okay, the third rule says if you've got an exponent on a log, you're allowed to just take and put it in front. So the exponent on your argument can go in front. Okay, here's an example. Log base 10 of 3 to the 5th is the same as 5 log base 10, 3. Okay, this last rule I want to look at for a second. Okay, I want to see why it's true. It's very, very simple why it's true. Okay, but I want you to understand it more than just taking an exponent and throwing it in front. Right, so let's look at this. Log of 3 to the 5th. What does 3 to the 5th mean? If I was going to write it without an exponent.
3 times 3 times 3 times 3.
Yeah, 3 times 3, 5 times. Right, now, yeah, we got 5. Right, this is really rule 1. Okay, if you look at it, it says if you have a product, you can split the product as a sum. I only wrote it for m times n. But if you had L times m times n, then you could put log base a of L plus log base a of m plus log base a of n. You can split it up into as many as you want. Right. So in this one, it's going to split into how many logs? 5, and they're all going to have what sign between them? Yeah, a bunch of pluses. What's the argument of my first log?
3.
Second one?
3.
Yeah, they're all 3. Now, I have log 3 plus log 3 5 times. How many log 3s do I have? I have 5 log 3s. That's why you can just take the exponent and put it in front. Right? So we're not going to go through this again. Okay, from now on, we'll just take the exponent and put it in front, but that's the reason why. It's just rule 1 extended. All right, so we got that. And last thing, I think we already mentioned this earlier in the week. You can write a square root as a fractional exponent. And you'll see where that comes up when we get to a problem. All right, so we're going to start out with the harder way first. Okay? We're going to take something that's nice and combined and start splitting it apart. Okay? I like going the other way because you're taking something that's already split apart and making it simpler as you go. Okay, so this is the opposite. Okay. Any powers that we have, they want them expressed as factors. So in other words, use rule 3. Don't leave powers as exponents. Put them in front. If you have an exponent. All right, so first thing I look at is my argument. Decide if it's multiplication or division. And then that tells me, does it split as a sum or difference? Okay, so how will this one split? Yep, it's a sum. We'll have a log. We'll have another log. What's going to be the base on each log?
4.
Yep, stays exactly what it was as the original. My first argument. Second argument. Done. That's it. Okay, these are all we're doing for the rest of class. We'll try a few splitting and then a few combining. Okay, they get a little harder, but you just use the same 3 rules. All right, so inside here, this is multiplication. So there's something a little bit more complicated, but it's something times something. So when we have multiplication, we split it up as a sum. We've got a log. Base on each log? 2. Yep.
5.
First argument is 5.
And then the 3 log base 2.
Yeah, if you want to do both steps at once, you can do it like that. Okay, before you do that step, it would be like this. You'd split it log base 2, 5 plus log base 2r cubed. Is everyone okay if I put the 3 in front all in one step? That's fine. Okay. If you need to do it in 2 steps, that's fine. Okay, how's this one going to split? Difference. Okay, it's going to be a difference. Log base 9 of x minus log base 9 of 2. Now, once we know how, log base 9 of 2, you can type that in if we want the decimal. Okay, we don't, but you could. This has a variable, so this you can't figure out. Yeah.
Are you going to teach that today or next week?
No, I'll teach you how to type that in next week.
It's a lot of suspension.
Yeah, you're going to have to wait.
Is this section going to be on the test form?
Oh, yes. Yep. Yep. Be five or six. Half the test will probably be close to half will be on logarithms.
Use logarithms today.
Yeah, maybe 5, 6 problems. Yep. The test is probably going to be about 14 questions.
Does it make almost as hard as the last one?
There'll be a mixture, yeah.
So the last one is I like the last one.
All right, now this one, before I even split it, what base am I using? E, that's fine. So when we split this up, just write it as ln's. Okay, ln minus or plus, whatever you think it is. Anybody give me the whole thing? Think you can do the split and moving anything that needs to be moved all in one step? Thinking about it? Kinda?
I'll do it.
Yeah?
Okay. 3 ln y
Mhm.
minus ln
Perfect. 3 ln y minus ln 8. Okay. If you wanted to do it in 2 steps, you'd start with y cubed, and then the 3 would go in front, minus because of the fraction.
So on the test, that doesn't ln form, and you want it like simplified. We leave it as ln. You
Yeah,
don't-
yeah.
You
Yep.
don't break it up.
Yep, leave it as ln, just like that.
Okay.
Don't write log base e or anything. Yep. And don't find the ln of 8. We could type it in, but I don't want it.
Can we use a capital so I don't think it's only one?
Yeah, I guess you could. You won't see it written as a capital, like when you press the buttons. They always use lowercase. Yeah, everything on this is capitals. They just use capitals for the whole calculator.
And
Yeah.
This one is okay.
I mean, like if we're doing it on the test, and if I put
You can put a capital, that's okay. Yep.
So for this test, if we put like ln, you won't mix it up with like 1n, right?
No,
Or it's 10g.
no, I know what I'm looking for, yeah. Yeah, like log 10g, yeah, I know what you mean.
Because that's been like my whole like thing this entire class. Like, oh, that kind of looks like 10g. Oh, that looks like 1n. I'm gonna mess
All right, so let's, this one I'm going to skip. We're going to go right to the last one.
Oh, God.
We're going to go right to the big leagues now.
Let's go back to the minors.
All right, so first thing, if I have something in parentheses, deal with the fraction first. Put the top separate and then the bottom separate. Just split that. So how does the fraction split?
Square root of log a, square root of x squared plus 1
All right, so you got the square root of x squared plus 1
minus
minus.
log a, x to the third times x plus 1 to the fourth.
Yep, all that stuff. You're never going to FOIL this out, okay? If you start FOILing out x plus 1 to the fourth, that's way too much work, okay? It's going to be much easier than that. Okay, but all I did was split it up as log of the top minus log of the bottom. Okay. Yep, just so we understand this whole thing is part of the log. This is all the argument. Everything.
Could you use double parentheses?
You could use double parentheses, yeah. Okay, now this. I don't like in logarithms to have square root symbols. I'd rather have exponents. So how can you rewrite square root of x squared plus 1. Yep.
Could you do 2 log a x plus x squared plus 1?
No, don't move anything in front yet. Just think of a square root is the same as what power? A half. That's all you have to do. Okay? And this one is just about done, except for one thing we have to do. Okay, but that'll be done. And now in this argument, what do we have here? Do we have more division or product? Yeah, you've got something times something. So split that up. Okay, what's going to be my first term when I split that up?
Log a
Log base A of
x plus 3.
x to the third. And again, we'll talk about doing something with that 3 symbol.
Plus x plus 1 log base a, x plus 1 to the 4th.
X plus 1 to the 4th. And again, there's one more thing we have to do. So what's the last thing we have to do in all 3 parts? Put all those exponents in front. Okay, you could have done that in this step in your head if you feel comfortable. If it's too much at once, just do it the way we did it. 1/2 log base A, x squared plus 1. I had some people try to do something with this. You can't. We don't have a rule when it's a plus. We have a rule when it's a product or when it's a fraction. Okay, so that's done. Minus, and you need these brackets because that minus is distributed to everything you just split out of this log. So minus log base A x, put the 3 in front, plus, put the 4 in front. Okay. You might see in the book, they could write this as minus 3 log minus 4. They could distribute it, but let's just leave it. Okay, and that's the hardest kind of log you have. So if you can do this one, you'll easily be able to do anything like this type on the test. I don't even think there's one quite as hard as this.
Should we make that an extra bonus question?
Okay, any question on that?
Was there any bonus questions on this?
I'll have to double check. I don't think so though.
100
think
points
so.
with no bonus credit.
100 extra points? Yeah.
Yeah, because I'm filling in a
Divided
zero on
by
the test.
100 times.
All right, so the last two we're going to do is just putting it back together. Okay. And this is generally easier because it's going to get smaller at each step. It's not going to get worse. So just do everything you just did in reverse. So what's the first thing you do here?
What is that?
Yeah.
Yeah, put the exponent to 3.
Yeah, put the 4 back up. Log base A of 7 plus, what would my argument be?
Oh, sorry, 3
3 to the 4th. Instead of leaving it as 3 to the 4th, just simplify it. 3 to the 4th power is 81. Okay.
What if we don't simplify?
Then it won't be fully done. Yeah, you got to simplify it as much as you can. Okay, now the last thing. This is split as a sum. What must it have been before you split it?
3 times 7.
Yeah, 7 times 81.
You have to make the
Calculator.
567.
Just know, yeah.
I just did 7 times 8 is 56, and then 7 times 1 is 7.
That works.
Yeah, I thought of it this way. 7 times 8 is 56. 7 times 1, 56, I just said. And then I have a 0 because it's not 7 times 8. It's 7 times 80, and then 7 times 1.
That's usually how
So I just did the distributed property in my head. So 567.
When you said just 7 times 8, that's why I was like confused. 'Cause I was like,
Yeah.
I think you meant 80, but I wasn't sure.
Yeah. Okay. So any question on that one?
45 times.
Yeah, it's 100.
You have to do that.
Oh my god.
You have to do that.
All right. And
Terrible example.
last one. Okay, I want to recombine that into a single log.
I don't want
Is that 71? That is 71, right?
71, yeah.
Well, that's 10.
Yeah, this part, I would just write this first.
I like
3 to the 4th is 81
Yeah.
minus 71. Don't leave it more complicated than it has to be. Just make it 10.
And then you have 8 to 2/3.
I'll add an 8 to the 2/3. Now, here's how you do a fractional exponent in your head. Okay, block off the denominator. What's 8 squared?
64.
64. Divide by 3 means cube root. Okay? What's the cube root of 64? 4. 4 times 4 times 4. Okay. If the number gets too big, you could just use your calculator. But this is one that does work out nicely. 8 squared is 4. 8 squared is 64. Cube root is 4.
So it's going to be ln 2/5.
Can you explain how you get 2/5? Because you are right.
Because you have to put 4 over 10.
Yeah.
So you can ln 2/5.
And then that reduces.
Yeah.
Okay, so on the test tomorrow, the last 6 or 7 problems are going to be on logs. Okay, so the homework is on 292. It's 1 to 7, 13 to 17, 21 to 27, and 29 through 33. Okay, we'll go over that tomorrow before the test. I will be after school today if anybody needs extra help. And then we can take a look at that last one.